Good morning. This is Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. I'm the organic chemistry instructor for the summer 1. Today we are going to start chapter 5. Chapter 5 over structure and preparation of alkene. We are going to study carbon-carbon double bond. So we are going to be more focusing on the preparations using the elimination reaction to produce alkene. So this lecture we are going to involve in totally 18 different topics. The first topic is about the nomenclature of alkene. If you have the hydrocarbon which involved in carbon-carbon double bond, this group of hydrocarbon is defined as alkene. And then we are going to study the structure and the bonding in alkene. Before we studied the hybridization, we do know when double bond between carbons formed, so you are going to take the sp2 hybridization. The carbon atoms is going to subject to the sp2 hybridization, meaning 1p orbital 2pz is unhybridized. And then we are going to study the different isomers in the alkene. In this case, involved in constitutional isomers and also stereoisomers. How do we name the stereoisomeric alkene? By using the EZ notational system. And then move on to the physical properties of alkene and the relatively stability of the alkene. Also, the cycloalkene is another topic. Cycloalkene and alkene, you can name them essentially the same way as you name your alkane. You simply change A and E from your alkane into the E and E for your alkene. And then we are going to briefly discussing about the preparation of alkene in this lecture. And then from next lecture, we are going to be more focusing on 4 different types of the elimination reactions, such as elimination of hydrogen from the alkane to produce alkene. You eliminate the H2O water from the alcohol, you call it dehydration. The first one called dehydrogenation. And then we are going to learn dehydration. We also can eliminate an HCl, HBr from your alcohol halides to produce alkene. You call it dehydrogenation. And also you may have some other alkene dehalogenation. If you have dihalo compounds, you have 2 different Cl. So in that case, you are going to remove a halogen. So you call it dehydrohalogenation. All of this elimination involved in 2 major mechanisms. One is called E1, second one called E2. You have E1, E2 related to the elimination reaction. We are going to discuss step by step about the mechanism. During the elimination reaction, for example, during your alcohol dehydration, so you are going to form different isomers. You are going to follow regioselectivity. So there is an important rule called the Ch5's rule, also called Jeff's rule, going to show you which of the OH hydrogen is going to be removed. In this case, remember one thing, we call the less the left. If you have your hydrogen which connected to the carbon, that hydrogen and OH will be removed if you have less hydrogen connected to the related carbon. So we are going to show you. And then as we mentioned, you have dehydrohalogenation of your alcohol halides and related to E1, E2 different eliminations. And we are going to do a little bit of comparison of E1, E2. And also the very last topic related to arrangement of your different types of carbocation. If you have primary carbocation, you may move in one of the methyl group to convert it to the secondary, or you may be involved in hydride shift to produce from a primary to secondary, further maybe even convert it into a tertiary carbocation. That's called rearrangement of the different groups during the alcohol dehydrogenation. Again, in terms of the production of preparation of alkene, you can produce alkene from alkane through dehydrogenation. You can produce alkene from alcohol through dehydration. You can produce alkene from alcohol halides through dehydrohalogenation. There is another one. You can also remove the halogens from your alcohol halides. Normally you need the dihalides. This one you call the dehalogenation. 4 different types of elimination. So first topic will be about the alkene nomenclature. You have 3 major steps. Step 1, you are going to identify the longest continuous carbon chain, which includes the carbon-carbon double bond. Step 2, you are going to replace the A and E ending of the corresponding unbranched alkane with E and E to name the alkene. A and E going to be changed to E and E, representing carbon-carbon double bond. And then you are going to number the carbon chain in the direction that gives the lowest number to the first carbon, to the double bonded first carbon. Normally you put your double bonded carbon as the smallest locants. For example, I have this molecule. I have carbon 1, 2, 3, 4. How do you name the carbons? You started with the double bonded carbon. And then this double bond is located between 1 and 2. You call it 1-butane. 1-butane is derived from butane. You change A and E to E and E. Also, you can call it bu1-ene. So the second molecule, you have totally 6 different carbons. How do you name these different carbons? In the direction from the right to the left. Therefore, give your double bonded carbons at the lowest locant. The double bonded carbon between 2 and 3, you name it as 2-hexene. 6 carbon derived from hexane. You change A and E to E and E. And then you label the carbon double bond, so as number 2, 2-hexene. So if you have different types of compounds, such as you have substituents, you have methyl substituents, you have propyl substituents, you have alcohol-based, which one has the higher priority? First of all, your alkene double bonds has the higher priority, takes the precedence over the longer chain which do not include the alkene, meaning double bond over the alkyl group. If you have your alkyl group, you again going to count the longest continuous carbon chain, and then double bond must be located in the smallest locant. Again, so if you have alkyl and halo, your alkene always takes the precedence over alcohol and halo substituents when numbering the carbons. This first example. So you start counting carbon from the double bonds. So from left to the right, carbon 1, 2, 3, 4. In the number 3, you have a methyl group. So this is your from your butane, you convert it to butene, double bond named as number 1. And then number 3 locant, you have a methyl group. You call it 3-methyl-1-butene. You can simply call it 3-methyl-butene. The second compound, let's see. So you have carbon, you have number 1, let's see, carbon 1, 2, 3, 4, 5, 6, 7 look like the longest one. However, your alkene carbon double bond takes precedence over the longest carbon-carbon chain without double bond. So again, so you name it as from here, double bonded carbon, number 1, 2, 3, 4, 5, 6. Therefore, you call this compound hexene. This is your hexene. And then you have substituents which composed of 1, 2, 3. 3 you call it is from propane, you call it propyl. So you have a carbon 3, you have propyl. And then this carbon 6, you have a bromo. So 6 is your bromo, 3 you have your propyl. How do you name the bromo and propyl? Based on alphabetic order. Bromo comes first, followed by the propyl. So this compound you call the 6-bromo 3-propyl hexene. So this number 1 you don't have to name it. You don't have to identify it, but you can. So 6-bromo 3-propyl 1-hexene. If you again have hydroxyl such as OH group, OH group overranks the alkene, overranks of your alcohol and hylose. So this molecule, how do we count the number? When you number the different carbons, the longest carbon-carbon chain composed of a double carbon double bond. So in this case, you start counting the carbon which connected to the OH. So there's 1, 2, 3, 4, 5, 6. Totally 6 number. This compound, you name it as from alkene, change the E to O. You consider this one is an enol. It's an enol. You change alkene, this E to OL. This suffix will be your enol. And then your OH located in the smallest locant. And then your double bonded carbon will be the second priority. This molecule is named as, you have a methyl in the 5th group, you call the 5-methyl, double carbon bond located in the 4 and the 5, you call the 4-hexene. Number 1, you can call it hexenol. So hexenol, which you have OH in the number 1 carbon, you have the hexene 1O, 5-methyl, 4-hexene 1O. So this is about your enol nomenclature. So you have oxygen. Oxygen is overranks the alkene. Double bond overrank alcohol. Double bond overrank hylose. So that's how you name the different alkene, substituted alkenes. And also there are some common names which are also acceptable. For example, you have this CH2. You call it, based on our IUPAC name, you have 2 carbon, you have ethene. This molecule also called isolene. You have this compound 1, 2, 3. It's a propene. You also call it propylene. And also we have something called vinyl groups, such as you have this CH2 double bond CH. You have this group. This is called a vinyl group. This molecule, if you have a Cl, chlorine connected, you name it as a chloride. This molecule called vinyl chloride. You also can have allo, carbon double bond, single bond, and a group, such as you have OH connected to this carbon, you call it allo alcohol. You also can have isopropanol. Isopropanol is PENYL. You also call it isopropanol chloride. This is a common name, so they can be accepted. If we have our cycloalkene, how we are going to name the compounds based on IUPAC naming convention. So first of all, you are going to change your corresponding cycloalkane into cycloalkene. Again, you change your ANE to ENE. And then if you don't have any substituents, therefore you don't have to worry about the locants. With the alkyl and halo substituents, again, you are going to number your alkene as carbon 1, carbon 2, and then moving to the methyl, iso, or the alkyl groups and halo groups. For example, the first one, let's count it. Number 1, number 2, 3, 4, 5 carbons. So this is cyclocarbon 5, you call it pentene. From cyclopentane, you convert it to cyclopentene. There is no substituents, no locant. So the second molecule, you name it based on the smallest carbon double bond locants. Carbon 1, 2, 3, 4, 5, 6. You call it 1-methyl cyclohexene. This third molecule, how do you name it? You start from double bonded carbon, put it in the number 1, number 2. Carbon 1, 2, 3, 4, 5, all the way 7. And your chloro is in the number 3 carbon. You call the 3-chlorocycloheptene. 3-chlorocycloheptene is a cyclo compound. So you don't name it as 1-chloro-2-cycloheptene. So this number chloro has a lower priority compared with carbon-carbon double bond. In your alkene, what is the bonding cases? What the structure look like? First of all, in your alkene, you are going to have, in terms of double bonds part, you are going to have a planar structure. Planar of double bonded carbon and the substituents should be located in the same plane, unless the carbon bond keep increasing. And then in your alkene, the carbon takes sp2 hybridization. And your alkene, as we mentioned, is a planar structure, such as in this A. This A showed you there's a double bond, and the carbon-carbon and the other 2 other bonds for each carbon, they are the planar structure. Just for example, the left-hand carbon, in terms of this part, that is the planar structure. May not be trigonal planar because you have carbon double bond, the bond angle between carbon hydrogen carbon double bond, so that is 121.4, and then double bond carbon double bond is 134 picometers. And then in your alkene, you have 2 types of bonding. You have sigma bond and 1-pi bond. Sigma bond and 1-pi bond. The 1-pi bond is made due to the overlap of the pz orbitals. Remember, you take sp2 hybridization, your x and y, they hybridized. The z orbital is leaving unchanged. And then, so in your alkene, as we mentioned, you have this sigma and pi bond. So pi bond overlapped from your p orbital, made from overlapping of the p orbitals, like we showed. This is the p orbital. So over here you do have a pi bond, the p orbital, that's a pi bond, and also have sigma bond. And the bond strengths of the carbon double bonds. Usually the double bond is stronger than the single bond and shorter than the single bond, but it's not twice of the strength of double bond is not twice of the single bond, meaning the pi bond is weaker than the sigma bond. Again, the double bond shorter than single bond. Single bond is 150 picometer, double bond 134 picometer. The double bond has strength, so stronger than the single bond, but it's not the twice in terms of the single bond energy. And then the isomers in your alkane can be quite complicated. For example, if I have one butane can have different isomers, totally 4 different isomers. So let's see, you can have a carbon 1, 2, 3, 4, all directly connected to each other. So double bond located in carbon 1, 2, you call the 1-butane. And then this 1-butane can have isomers based on C4H8. So if you just have C4H8 for alkene, without considering cycloalkane, we didn't consider compare with cycloalkane. The second molecule for this C4H8 in terms of alkene, so you have this, say, C carbon, and this second carbon, you are going to have 2 substituents. So this molecule and the first one, they are called constitutional isomers. And then you can also move your carbon double bond between 2 and 3. So you have carbon 1, 2, 3, 4. So this is also butane, but the carbon double bond between 2 and 3 you called 2-butane. And this 2 methyl group, the same group, you put them into the same side of the carbon double bond. Therefore, you call the cis-2-butane. Also, these 2 methyl, the similar or the same groups, you put them opposite to each other. In this case, you have trans-2-butane. You have these 4 different isomers for C4H8. So butane is one of the isomer, and your 3-methyl butane, this molecule is called constitutional isomer compared with the other ones. So these 2, you call them stereoisomers. Cis and trans, they both can be existing, but cis and trans, they cannot be inter-exchange. Your cis cannot be subject to the conversion becomes to the trans. They cannot. The reason is you have your pi bond formation. The rotation about the double bond is restricted due to the p orbital overlap. So therefore, no interconversion between the cis-trans 2-butane isomers. This part we need to know it. Sometimes in the nomenclature, so you have 2 complicated substituents. So therefore, you cannot simply use cis or trans naming convention. So in this case, we can use EZ nomenclature, naming stereoisomeric alkene by the EZ notation system. So again, because your substituents becomes very complicated, so you are going to use the EZ system. So what you need to know, you need to identify which substituent has the higher priority. First of all, hydrogen has the lowest priority, and then your halogens and the alkyl groups, such as methyl, isopropyl, they have lower priority. Among the same halogens, you have fluoro, chloro, bromo, iodo. So which one has a higher priority depends on the atomic number. So you have fluoro and bromo. So when you're discussing the higher priority, you're discussing this 1, 2, 3, 4. 3 and 4, these two you discuss. Fluoro compared with bromo. Bromo has a larger atomic number, therefore bromo has a bigger or higher priority. The chloro and this hydrogen, chloro has a bigger atomic number, chloro has a higher priority. So therefore, when you put two higher priority on the same side of your carbon double bond, like your bromo and chloro, so they are the groups in the same side. So therefore, you call this called the Z configuration. Otherwise, if you switch position between this bromo and fluoro, you call it E conformation. And then or configuration. The second group, if I have this molecule, that's what I write it down. So technically, you simply rotate bromo and fluoro. So you switch bromo and fluoro. Therefore, two higher priority substituents are located in the opposite side of carbon double bond. You call this structure E configuration. To summarize about this EZ configuration, so number one, the two atoms directly connected to each alkene are going to be compared. You're not going to compare further away. You compare bromo, chloro, aldo, hydrogen. If there's chloro connected to something else, you are going to compare afterwards. The atom with a higher atomic number has the higher priority. And then the position such as chloro-bromo, the position of high priority groups are going to be compared. So if the high priority groups are located on the same side of your carbon-carbon double bond, you call it Z configuration. If the higher priority groups, so such as chloro-bromo, they're located in the opposite side, you call it E configuration. This is about EZ configuration, about the nomenclature. We just discussed the atoms. If you don't only have an atom as a group, such as this molecule, I have bromo, chloro, and also I have methyl and iso. How do you compare it? So you are going to use a system called Kahn-Ingold prelog system. Kahn-Ingold prelog system is going to indicate which group has the higher priority. So let's see. So when two atoms attach to the same carbon of the double bond, if they are identical, such as, so carbon, double bonded carbon, you have carbon, carbon, the first atom, the both carbons, what you are going to do? They are identical. Therefore, you compare the atoms connected to that carbon. So this carbon, the pink colored carbon connected to 3 hydrogens. This indigo colored carbon connected to 2 hydrogen and 1 carbon. In this case, this iso will have a higher priority. So the priority you are going to determine based on the precedence determined at the first point of the difference. Come to the first point of the difference. So you see this compound is Z or E configuration. So bromo compared with chloro, bromo has higher priority. Methyl compared with iso has priority. Therefore, your two larger group or two groups with higher priority located in the opposite position, you call that one is an E configuration. Let's see this molecule. This molecule you also have chloro-bromo, both BrCl connected to double bonded carbon. So bromo again has a higher priority because bromo has a higher atomic number. How about this group? So you have a carbon connected to 2 hydrogen and 1 carbon. This group, carbon connected to 1 hydrogen and 2 other carbons. carbon connected to one carbon, two hydrogen, carbon connected to two carbon and one hydrogen. So the first point of difference is a carbon and hydrogen. Therefore, this group has higher priority. This configuration, the left-hand configuration, you call the E configuration. So again, you are not going to consider oxygen. Oxygen is not going to be counted because oxygen is not located in your first point. It's not the first point of difference. The first point of difference reached to the first carbon. So this is a carbon, they both the same. Your first point of difference is this pink colored carbon and this indigo colored carbon. Oxygen is located in your second carbon. Let's see this group. This group, you have a bromo, chloro, no argument. And then you have carbon connected to two hydrogens and one oxygen. This carbon, you connected directly to three carbons. So in this case, your oxygen, you can count it no matter what. You have oxygen and carbon connected to two hydrogens. So oxygen again is like this oxygen, carbon connected to carbon, oxygen, carbon connected to carbon. Your carbon connected to the oxygen, whenever you have this alcohol group, OH group overrank the methyl groups. So therefore, this first one, so they are going to be considered the higher priority. This molecule is considered the configuration. So in this case, your first point of difference is resulted from oxygen and carbon. Oxygen has a larger atomic number. Oxygen is going to have a higher priority. So that's what we are going to determine about the EZ configuration. So and then if you know the EZ configuration, you know the nomenclature, we need also to know the physical properties of alkene. So the first property is called dipole moments. Dipole moments is resulted from the geometry of molecule and also the polar bonds, bond polarity. So the molecular dipole moment is the sum of the vector of your bond dipole moments. Your vinyl halides, they have a dipole towards to the more electronegative chlorine. If you, for example, I have 4 different compounds. I have isolene, I have vinyl chloro, I have propene, I have a trans 1-chloropropene. Which one is going to have the bond polarity? Let's see. This ethane, carbon, hydrogen have polarity, polar bonds. However, they all cancelled out. So this isolene is a non-polar molecule. If one of these hydrogen replaced by chlorine, so you receive a vinyl chloride. What's going to happen? This carbon-hydrogen bond, this carbon-hydrogen may cancel out. However, your carbon chlorine, this bond is much, bond polarity is much stronger, and then the polarity pointed from the carbon to the chlorine. The bond, the dipole moment for this molecule is 1.4 dpi. If you have a CH3, this is called electron donating group. Methyl group is considered electron donating, meaning this dipole moment is going to point it from the methyl carbon towards the double bonded carbon. Therefore, this molecule, this propene is also a polar molecule because carbon-carbon that bond electronegativity is essentially the same. The methyl carbon dipole and the carbon hydrogen dipole, they are very the difference is not very significant. So this molecule has a very small dipole moment, 0.3 dpi. If you have one of the hydrogen replaced by chlorine from your propane, you form a trans 1-chloropropene. In this case, what you are going to have? You have a dipole pointed from methyl carbon to double bonded carbon pointed to the chlorine. So you have very high dipole moment for this trans 1-chloropropene. So that's how you determine the dipole moment. About the stability of different alkene, you can determine it based on the cis-trans isomers. Also, you can use the heat of combustion of the alkene to determine it. Usually, if this heat of combustion, this value, the bigger this value is, the less stable this compound. In other words, you are going to take a look of substituents. The more substituents you have, the stable the molecule is. This 2-methylpropene has the most has 2 methyl substituents for one of the double bonded carbon. So this one has the smallest heat of combustion in kilojoules per mole. About the stability of your alkene, usually can be considered governed by these several factors. The first factor, called the electronic effect, the degree of the substitution of the carbon-carbon bond. That's the first priority. The more substitution you have, the more stable the molecule is. The second important factor is called a steric effect. The van der Waals strain particularly in the cis stereoisomer is going to be critical. You want to put your two different groups in the opposite side. So meaning the trans theoretically should be more stable than cis. And then also the chain branching. If you have the chain, the longer branching, usually the stability should be increased. So the highly substituted double bonded are usually more stable compared with the less substituted double bond. And the trans alkene usually are more stable than the cis stereoisomer. If you have the cycloalkene, you need to pay attention. Sometimes cis may be more stable, so be careful with this point. Stability of the alkene, let's see a little bit different. So you have this different compounds, so the most substituted, the more stable. The trans compared with the cis is also more stable. So and then about the cyclohexene, how do we determine or name the cyclohexene? So you are essentially naming it as the cycloalkane. So this 3-numbered cyclo compound you call the cyclopropene. Fourth one, cyclobutene, cyclohexene, cyclopentene, cyclohexene. Sorry for these two, this is supposed to be two different names. And your cyclohexene actually exists as the half trial structure. If you have a bigger ones, you have say cyclooctane. This cyclooctane, you can have E configuration, trans configuration, you also can have Z configuration. What we found that the cis cyclohexene was found more stable. So again, if you have cyclohexalkene, so pay attention to the cis and trans. Trans may not have the higher stability. You can double check why is that, because you can put the larger groups in the different positions. And then followed by, we are going to learn about preparation synthesis of alkenes using the elimination reactions E1 and E2. So here is a summary. You can use the dehydrogenation of alkane to produce an alkene. You remove 2 hydrogens from 2 different carbons from the neighboring carbon called alpha beta, called beta elimination. So dehydrogenation, to remove a hydrogen molecule. Normally this reaction is under high temperature, is an industry processing. The second reaction called the dehydration of your alcohol. You are going to remove a water molecule, and this reaction is also a beta elimination and is usually catalyzed by the strong acid, this reaction can be a homogeneous catalytic reaction. The third one is also a beta elimination called dehydrohalogenation of alkyl halides to produce an alkene. This reaction usually you need a strong base such as sodium alkoxide is needed. This reaction usually follow the Ch5 rule. Also you have dehydrohalogenation dehalogenation of dihaloalkene. You have alkyl halides, you have two halides. In this case, you may need another strong base called alcoholic KOH is needed. That's generally about the different elimination reactions to produce alkene. So next class, we are going to go through different types of elimination. Also, two different types of mechanism, E1 and E2. So today, I will call it a day for today. Thank you so much for listening. You have a beautiful day. Stay safe and healthy.